Get more information on this and other astrophotography tips, articles, and tutorials at the PhotographingSpace.com website. And don't forget to sign up for our weekly tips newsletter and subscribe to our YouTube channel for more tutorials and video.
Welcome to my PowerPoint presentation and video of deep sky imaging, and it's a very brief guide. What this isn't is a cover-all guide so that you can go out there and start collecting data and start creating fantastic deep sky images straight away. There's plenty of books out there, there's plenty of information on the internet, and this really is just a very, very brief guide for anybody who may be interested in it and how it's done. Okay, so deep sky imaging, how it works is that you want to be looking at getting as much data and as much exposure as you can on a target in the sky that actually you can't see. 9 times out of 10 you can't see it. I know that sounds really, really strange, but the light from these targets has taken many millions of years, thousands of years to arrive here. They're very, very faint, and most of the time, apart from the odd deep sky targets such as Andromeda or the Orion Nebula, for example, most of the time they are invisible to our eyes. So what we want to do is we want to get as many exposures as possible, and we want to get them for as long as possible. And what this does is it ensures that your your signal to noise ratio is sufficient so that when you start processing, you will actually see something on the screen. Also, with deep sky imaging, unless you actually want to produce an image of star trails, and there are many out there, and I think they're very, very good, but this isn't being covered for the purposes of this this guide. You want to get your stars nice and round. They're pinpoints after all. They're not elongated worms or maggots or anything else. They are pinpoints. So you want to make sure that you keep your exposures nice and short so that you can maximize the stars and make sure that you get them nice and round. They want to be short enough so that your stars don't become anything other than round. Okay, there's some free software out there to help. Always good to use free software if you can. The links here are on the screen. Deep Sky Stacker, that is software where you put all of your exposures into the program, and it does wonderful things, and then it spits out an image that you are then ready to start processing with. The image is going to be black. There's one as an example in here further down through the guide. It's just a starter. From there, you do need to process. GIMP, again, the email address is there, and that's a free processing software that you can use. It may well be that you already have Photoshop or Lightroom or something like that, in which case that's all well and good, and I use Photoshop for most of my processing. But if you don't, Photoshop can be expensive, and GIMP is free software that you can download. There's also their Carts2CL and Stellarium, again free to download, and they're planetarium software programs. So you can have a look up, you can set the day, the time of your night sky, and you can have a look and see what sort of thing you might be able to see. Okay, stacking. This really is the crux of deep sky imaging. As you can see here, I've just given a brief example of 5 different images. And what you do is basically, or the software does, is basically puts them one on top of the other, and then on the right-hand side, you can see the sort of image that you get out of the stack. It's black, you can see a couple of bright stars, there's nothing to it, you can't see anything in there, that's where the processing comes in. This guide is not going to cover the processing. The processing is something that will be looked at further on down the line in one of the guides that we're looking at doing with the online Astronomy Society. Okay, the different components in imaging. Well, the main thing is the German equatorial mount. I started off using an HEQ5 by Skywatcher. You need a mount that is able to track. It needs motors in the RA and the deck axis. It needs to be able to be hooked up to a computer. It needs to have an auto guide port, because eventually you need to be looking at long exposures is guiding, and we'll cover that a little bit further on. Here I've outlined two main sort of ways really of looking at deep sky imaging. On the left is with a DSLR. A DSLR and an intervalometer means you actually don't even need a computer, because you can take your pictures. They go onto the card in the camera, and the intervalometer means that you can set X number of exposures at X amount of time. So you don't even need a computer for that. There's a wide angle lens on the DSLR, so you could use that for Milky Way shots, for example. You don't even need to hook up anything to a telescope. The telescope, obviously, you can use, and I just think of a telescope as a very long camera lens. In reality, the camera goes onto the back of it and off you go. On the right-hand side, excuse me, I don't know my left from my right, is the other way, and the way that I've ended up now doing my deep sky imaging is with a CCD camera. And you can see there, a CCD camera looks nothing like a camera. You can see the sensor in there. If you go for a mono, because there's two types, there's a one-shot color or a mono. If you go for a mono, you need a filter wheel and you need color filters, because that's how you end up colorizing your image. Okay, so here's just a couple of examples really, different ways to image the sky. Here's ones that I've done. I don't make any excuses for the quality of them. This is when I first started out. So this is with a DSLR, a static tripod and a wide angle lens. Single shot of the Orion Nebula. You can see the details there on the screen. This was only a single shot. It wasn't even used with stacking or anything. So this really is probably about as basic as you can get. Okay, I then moved on to the tracking mount, so the German equatorial mount, as I've mentioned, a DSLR and a lens, a camera lens, and this was taken with a 300 millimeter Canon lens. And this was stacked. So as you can see there, you've got all the details there of how many exposures I took and for how long. The length of the exposures can be longer with a tracking mount, because the mount tracks the sky and will keep your stars rounder for longer, as opposed to a static tripod. The length of the subs, I think they weren't intentional to be like 44 seconds or 91 seconds. I think it was just something playing up, and that was how they ended up. Here, what you do is you take a lot of exposures, you stack them, and for M31 definitely, and a few other targets, you take short exposures as well, because there is a massive dynamic range difference in between the core and between the outer details. And if you want to capture it all, if you want to have a nice core and nice outer details, then you need to be looking at doing short exposures as well as longer exposures. You put them individually into Deep Sky Stacker, for example, and it gives you, in this instance, it will give you 7 individual images. So each one of these have been stacked. So all the 91 seconds have all been stacked together. The 44 seconds have all been stacked together. Gives you 7 individual images, and you then process them and then blend them in together. You don't put the different exposure times all together to come out as one stack. So once you start getting into this sort of game, it does take you a little bit longer, a little bit more effort, and certainly processing is a lot more effort. Okay, another popular one for people as they start out is M42. Like M41, popular because it's nice and big, you can see it, but as a beginner, these two are probably the hardest images that you can hope to take pictures of. Certainly they're images that I haven't gone back to in 4 years, because they're very, very difficult. Again, this was taken with a DSLR, the tracking mount, but this time it was taken with a telescope. That was a Skywatcher 120 ED telescope. So it was taken at approximately 900 millimeters of focal length. And again, it was done the same way as M31, although I don't have the details, where there was shorter exposure times for the core and longer exposure times for the outer area. So there you can either use the DSLR static tripod and a wide-angle lens, for example, which a lot of people will already have. You could use the DSLR and a lens on a tracking mount, or you can go the whole caboose and use a telescope. This one is the final way, really, which is the tracking mount and the telescope, but instead of a DSLR camera now, this is a astro-specific CCD camera. Like the picture that you saw before on the right-hand side, looks nothing like a camera, but it cooling prevents noise, or helps prevent noise. Looks nothing like a camera, and you do need a computer to be able to run it. Once you start looking at a CCD camera, and then you are going down the road of needing a laptop. Okay, so with a CCD, I'll concentrate on that because this is what I use, and this is hopefully where people, when they really do want to take good deep sky images, where they ultimately end up. So a mono CCD, as the name suggests, it's a mono sensor, black and white. There's no colour in it at all. And what you do in order to build up an image is, first of all, you take luminance data. Luminance data is black and white data that collects all of the detail from the target that you're looking at. It collects it across all wavelengths. You then use a filter wheel and filter different filters, different colours. You then collect your red data, your green data, and your blue data. And we look at that further on in this guide, and you can see that different filters allow different wavelengths of light through them. And I will also show you how you can see the difference that you can get using different filters, and you can see the effects of allowing different wavelengths in. So on the right is a luminance red, green, blue image. Again, totally unprocessed, and that is a sort of thing that you can start with once you start your processing journey. Okay, this is my current imaging kit. I use two telescopes. On the left is my refractor telescope. That's a wide field telescope and gives me a focal length of 330 millimeters, there or thereabouts. And on the right is an optimized Dow-Kirkham telescope, which gives me a focal length of 1,700 millimeters or 1.7 meters. A lot of the targets that we look at in deep sky imaging are very big, and a lot of them are very small. And so I find that having two scopes allows me to focus on the larger stuff and the smaller stuff. Unfortunately, there isn't really a one scope does it all. There isn't a one scope does it all focal length. The big stuff needs the shorter focal lengths, and it's as simple as that, really. Here you can see the camera as well on the back. This is a QSI camera. Doesn't look anything like a camera if you're used to a DSLR. Okay, long exposures, what it involves. In order to get the detail on your camera sensor, you will benefit hugely from long exposures. When I say long exposures, I, as a norm, use 30 minutes. So imagine, if you can, just your normal camera, you click the shutter, it takes a picture of your best mate, takes a picture of your selfie, whatever, and the shutter closes again, and that is probably 1/200th of a second that the shutter is open. What I'm doing here is I'm opening the shutter, it stays open for a period of 30 minutes, and then it closes. So if you can imagine, what you need to achieve in deep sky imaging is that the target needs to stay in exactly the same place for that whole 30 minutes, which is where tracking and where guiding comes into it. If it doesn't stay in the same place, and then your image is going to be blurred and you're not going to have very good detail in it. So in order to get your long exposures, you really do need to look at guiding. And here I've shown the probably one of the most popular software. Again, this is a free download, PhD, which stands for Push Here Dummy. And it is probably the simplest and the most widely used software in order for you to guide. But you do need a laptop, and it will take a lot of cables. So you basically need a separate scope. You've got your imaging scope, and you basically need a separate scope and guide camera that sends information back to the mount and tells it to move this amount, that amount. So here you can see, this is my refractor, and here is my separate guide scope. So it's connected to the top of the camera, and it has a separate camera out the back, which would normally all be connected up with cables, and the cables go via the computer ultimately to the mount, saying please move the mount this amount in order to be able to keep this star in the right place. The other option is an off-axis guider, which is used more often for much longer focal lengths. You can see it here. This is on the refractor again, and that is the camera and the off-axis guider. So you can see that there's a separate camera in there. That's what's sticking upwards, and that is connected to, again, via the computer to the mount to say, please move this amount of pixels. So putting it all together, once you've got everything together, once you've got your kit all together and all talking, you then need to think about how you're actually going to capture this data. 9 times out of 10, these programs aren't free programs. There are some cameras you buy that come bundled with their own software so that you can get going and you can, via the computer, you can say, please capture 30 exposures at 25 minutes. But most of them don't come with any kind of software at all, so you need to have software in place that is going to cost you. I use SG Pro. It's a program that allows you to say how many exposures you want, what filters to use. It plate solves, so it gets you back to the same place night after night, and it also ensures that with the help of an automatic focuser, again another gadget that goes on and allows you to maintain focus all night. I wake up in the morning with, cloud permitting, weather permitting, I wake up in the morning with an amount of data to process. So this is a good piece of software. It's a bit difficult to familiarise yourself with. It's a bit difficult to get going. It doesn't guide. There is some software out there you buy that is a complete package. So it gives you your data capture, it gives you your guiding, it gives you a little bit of processing to start with. This software is specifically for data capture, and then you use it in conjunction with PhD in order to get it guided. So field of view, what kind of scope and what kind of camera combination to use? As I said, there are some targets that are big and some targets that are small. That sounds a bit kind of blasé really, but it's very, very true. On the left-hand side, with my one scope at 330 millimeters, if I wanted to take a picture of Orion, that shows you how big the picture of Orion would be in my frame of my camera. That's the square. If I then used another scope, in this instance it was 1600 millimeters because I did this when I had a different scope, you can see that Orion would be totally frame filling, and if I wanted to take the complete nebula, and then I'd be having to look at mosaics, the complete nebula just doesn't fit into 1600 millimeters. So you need to be thinking about the kind of nebulas that you want to take pictures of, if they're generally the big ones or the smaller ones, and then you then look at a camera and a telescope combination in order to do that. Okay, how you plan a target. Targets respond to different wavelengths of light. What I've put here is narrowband or LRGB filters. Narrowband are a different wavelength to LRGB and basically allow you to process things very, very differently. They're what we would class as false colours. Some targets, so for example galaxies, have very, very little in the way of narrowband light in them. And so you could hammer away at it for 100 hours and you would end up with nothing in your picture at all because it just isn't there. How long to expose for? Well, I tend to try and expose for as long as I possibly can. So in my narrowband images, I expose for 30 minutes without fail. And when I'm doing broadband, that is luminance red, green or blue, I generally look at 10 minutes. How many exposures to take? Well, I just look at trying to take as many as I can. I generally set myself a target of maybe 40, 50, 60 exposures, and the weather plays up, I lose the will to live, I get impatient, and I end up with a lot less. That does depend somewhat on your telescope that you're using, the speed of your telescope. So, for example, my two telescopes are very different in speed. One is f3.9, which means it's very, very good at capturing light as quickly as possible. It's a very fast telescope. And my other is at 6.8, which is much slower. So in order to get the same amount of data, or detail rather, on the slower scope, I need to expose for longer. What you can do instead is just use more exposures. So what I've learned is that my f6.8 scope generally benefits from about, in narrowband, generally benefits from about 25 30-minute exposures. And that is something that I've just learnt with time and experience. My smaller scope, I can get away with maybe 8 hours in total, so 15 or 16 will give me a reasonable image. How many nights it will take, as I said. At some stage, you give up the will to live, you've attacked the same target for 6, 7, 8, 9, 10 nights. It's just something that you need to think about, really, on how long things will take. Data from previous year and data from a previous scope. There is software out there that will enable you to scale your data so that the data from one scope at one focal length will match the data from another scope at another focal length. So you can mix and match. If you've got a load of data from one scope from a previous year, and this year you've got a different scope or a different focal length or a different camera that gives you a different field of view, then you can use software in order to match them so you can carry on building. So it's just something, you really can add on to stuff year after year. Does the target fit into the field of view? That's going back to the slide before, showing you the different camera and telescope combinations. Pick your target wisely. Does it fit in the field of view? Are you actually going to get as much of the target in as you want? So here's differences in filters, as I mentioned. The luminance filter allows all wavelengths through, so basically you use that as your detail. Imagine, if you can, that you're painting and you gather your red, green and blue data and you make a base, I call it like a base layer, like a colour wash if you like, and then you add your luminance data on top of that, and it puts the detail into the colour. So you have your base layer, which is like your colour, and then your luminance on top gives you the detail within that colour. So here's a graph here that shows you the different wavelengths, and then on the right hand side it just gives you those different wavelengths as well. So as you can see, for example, hydrogen alpha is on a wavelength of 656 nanometers. So your filter will only allow light through at that wavelength. You get different filters, different strengths is probably the easiest word to use. So it does let a little bit of light through either side of that, but generally that's the sort of area that you're looking at. So your red, for example, is much broader. This is why they're called broadband filters, because here you're allowing at least 100 nanometers of light through with red, green and blue. And with your narrowband filters, your HB, your O3, your HA and your S2, you're allowing a very, very narrow amount of light through. So here's an example of how things look differently, or how things look different with different filters. So here you can see that on your going from left to right, this is HA data. So this is hydrogen alpha data taken through a narrowband hydrogen alpha filter. Then you've got O3, that's oxygen 3, and sulfur 2. You can see, certainly with sulfur 2, you can see the massive difference in the actual wavelength of light. So the data, the detail that it allows through, it's very, very different. And this is how you build up a colour image, because you then stack these later on, you put them into the right channels, and from there you get a colour image. And that's how you could get, say, for example, some areas of blue, some areas of red, because different filters react to different wavelengths of light. Before I mentioned about field of view, and I mentioned about making sure that your target fits onto your frame. If it doesn't, and then what you have to consider is making a mosaic. And here is an example. This is a mosaic that I did, which is 3 frames across and 2 frames down in depth. So a mosaic of 6 panes. What this doesn't show here is the overlap, but basically you take your 6 panes and then you stitch them together. And anybody who does anything with photography and maybe panoramic shots or something will probably have come across stitching. And here is a different example. This was only a 3-pane mosaic, but here this gives you an idea of how you stitch things together. So you need an overlap because it will register the stars on the image on the right, for example, the actual horse head. It will register those stars with the image in the middle, and that's how it stitches it all together. Okay. So other potential issues. How easy is all of this, and what else have you got to contend with? So what I've told you isn't bad enough. You've got light pollution. Unfortunately, nowhere, or there aren't a massive amount of dark sites, certainly not in the UK. You will have light pollution, and there are filters to combat this, but you do need to consider this. In some scopes, you get reflection, so you have a very, very bright star, and then becomes a massive reflection, and you then have to deal with them, or maybe think about having to put that star outside of the frame so you don't get reflections. Time and season sounds pretty obvious, but as the sky moves, there are certain times of the year when you can't see certain constellations. So, for example, Orion is a winter constellation. Cygnus in the Milky Way is a summer constellation. The moon is a killer for deep sky images. It makes the background very, very bright. And so you imagine that your light is coming to your camera from your target, and it's a very, very faint target already. The background brightness with the moon is probably higher than the target that is coming to your sensor. Therefore, you pick up a lot less detail because the moon is in effect washing all of that detail out. The wind is worth thinking about as well, because sometimes if you've got a big scope on your mount, it can act as a sail, and sometimes you can be guiding. A gust of wind just pushes the guide star out, and you're going to end up throwing away exposures because of that. Something to think about as well is that people have to set up and take down after every session. A lot of people have an observatory. I have an observatory, so I can be up and running within a matter of minutes once everything's cooled down. But it's worth thinking about if you have to carry your stuff to a site, if you have to get it downstairs, if you live in a flat, if you have to go to a dark site and transport it. These are things worth thinking about. And general conditions as well. Humidity tends to be fairly high in the UK. Humidity gives you dew. Humidity is going to affect your seeing. So when you look up and you see a star twinkling, you might think how nice it looks, but all I'm thinking of is that's going through the atmosphere. That's not giving me very, very good sky conditions. And so I'm going to be struggling to be able to get decent data. So if you've stuck with this and you thought that you might like to give deep sky imaging a go, and then there's just a couple of examples here after this slide showing you the sorts of images that you can get, certainly ones that I've taken, that involves a lot of lengthy processing that hopefully will get covered in another issue. So thank you very much for your time. I hope you enjoyed it. I hope that it made sense. And now just enjoy the pictures.
Get more information on this and other astrophotography tips, articles, and tutorials at the PhotographingSpace.com website. And don't forget to sign up for our weekly tips newsletter and subscribe to our YouTube channel for more tutorials and video.